The strong principle of mathematical induction, sometimes called complete induction, is a more powerful tool for induction proof. It goes as follows. Suppose that Pn is a statement about the positive integers. That's the same as what we've done before. And we have two properties we have to prove, a basis step and an inductive proof. So they are as follows. If P1 is a true statement, and whenever Pj is true for j equals 1 up through k, now that part's different, then Pk plus 1 is also true. Then, as a consequence, Pn is true for all positive integers n. So the difference is, rather than just assuming Pk is true here, we can assume that P of j is true all the way from 1 up through k, not just for Pk, but all of these. We can use any one of those in our proof to show that Pk plus 1 is true. Now that should make some sense, because if we know that P1 is true, and we know that whenever we know all the that P is true for all the integers up through k, this implies that it's true for P for k plus 1 as well, then it must be true for all positive integers. There's no place where the string breaks, because we can always go from all the previous ones to the next one. Not just one to the next, but all the previous ones to the next one. So it's just an equivalent statement of mathematical induction. We won't prove the equivalence here, but it is equivalent to the regular induction statement. It just gives us more that we can use when we are proving certain facts. So I'm going to show you an example of this. And so here we go. Here's the example. Every integer n greater than 1 is either a prime number or a product of prime numbers. Okay, notice I've got n greater than 1. 1 is not prime. We exclude it from the prime numbers by definition. Our definition excludes it. So we really do have to start with 2 here if we want to talk about numbers that are prime or products of prime. So let's dive in. Let Pn be a statement, the statement that n is a prime number or a product of prime numbers, because that's what we want to prove for all integers greater than 1. So Pn, remember, that's not a function. It's just a label for the nth statement that we're looking at. So the basis step here is not n equals 1, but n equals 2. So I'll just say since 2 is prime, P of 2 is definitely true. Right? Because P of 2 would say that 2 is a prime number or a product of primes. Well, it's prime. So that's true. That's all we need for the basis step. Now let's look at the inductive step, and I think I've written the whole thing out. That's okay. We'll just go through it and see what it says. So the inductive step this time would take k to be an integer such that k is greater than or equal to 2, because that's where our basis step started. And we'll assume that each integer, 2, 3, up through k, is either a prime or a product of prime numbers. That's true for each one of them. So this is P of 2, P of 3, P of 4. We're assuming all of these are true up to P of k. That is, each of the integers 2, 3, 4, up through k is a prime or a product of primes. Now we'll try to prove from this that k plus 1 satisfies the property. That is to say, either k plus 1 is prime or it's a product of primes. Well, we'll break it into cases. If k plus 1 is prime, then we're done. K plus 1 is true because it's prime. Otherwise, k plus 1 is not prime, so it means it's a product of numbers. It is divisible, let's put it that way, by something other than 1 in itself. So that other than 1 in itself, I'll call a. It's divisible by a, which is neither 1 nor k plus 1. Okay, so that means that a is a number between 1 and k plus 1. Now the quotient has to be some b that's also between 1 and k plus 1. Right? So if we have k plus 1 and we're defining it by a, Then we'll get a b with a remainder of 2. So k plus 1 is a times b. But since a is not 1, then b is not k plus 1. And since a is not k plus 1, then b is not 1. So b is also in between those. And k plus 1 is equal to a times b. It's a product of these two right here. By the induction assumption, each of a and b is either prime or a product of primes. Why is that? Well, because a and b are both in this collection 2 to k, right? That's equivalent to saying 2 to k inclusively, 2 to k inclusively. So they're either each of them is either prime or a product of primes. But that means when we multiply them together, k plus 1 equals a times b is a product of primes. Therefore, p of k plus 1 is true in this case as well. It's a product of primes. So what does this say? This says that if we assume all of these properties, that p of 2, p of 3, all the way up through p of k are true, these together imply that p of k plus 1 is true. And that's what the strong induction property allows us to do. That's enough to say that by the strong principle of mathematical induction, every integer n greater than 1 is either a prime number or a product of prime numbers. So that's one example of where strong induction can be used, and I'll try to come up with some examples for you to work on too.